All right, let's try this element distinctness problem. And we're actually doing a little bit of a variation of it. First, let's explain the problem. It is, so given an array, like let's say, of some amount of elements, can you tell if they're distinct? So say we're given an array 5, that's not exactly 5, 7, 3, 2, right? And then we have one of two answers. Is this yes, everything's distinct, or no, not every element is distinct? In this case, it's yes, but if we had a slightly different array, 5, 7, let's put another 5, 2, right? We have duplicate 5s here, so the answer is no, right? Let's say, though, the amount of elements in elements is either infinitely large or sufficiently large that it's just a pain to try to visually inspect yourself, right? One brute force way of doing this is we know that arrays can be sorted in log base 2 in time, right, with merge sort. So if we were to sort the first array, we'd have what, 2, 3, 5, and 7, right? Then from here we can compare maybe like index I to I plus 1, right? Then compare 3 to 5, and then 5 to 7, right? This, and then yeah, all right, so yeah, for this one, we know we'd have the total time complexity would be something like n log n. This is to sort it, right? Then plus really n minus 1, because we never compare 7 with anything, kind of maybe depending how this imaginary code is set up, but so then we'd have essentially n minus 1 work to go through the array, and then plus whatever our constants are, right? Whatever the kind of operations are. This gives us, though, a big O runtime of n log n, right? Because really this is the domineering term. The question, kind of the version of this element distinctness problem that we're kind of doing, then the kind of question that can arise is, can we do it in little o of n log n squared time? So at most, this is kind of this loose upper bound. I grabbed this picture off of Geeks for Geeks as kind of as like a little bit of a visual aid. We're used to seeing like x, I don't know, well, let's say 3x squared plus some x plus some, whatever, 2 or something, right? And then we would say the big O is x squared, because it's this loose upper bound, right? So we want to see if we can do it in little o time, without essentially kind of this comparison. I should have clarified comparison-based sort kind of method, because this n log n comes from merge sort, which is a comparison-based sort, which I'm sure we've proved before is the fastest we can do is n log 2 in time. If we use something like radix sort, that could be in k time, where k is the amount of digits in the largest number or something. But we're trying to prove little o in log n time without this kind of comparison-based sort method. One way we can do this is if we had some sort of array or structure in such a way that we had the outcomes kind of planned. And I think we can start to visualize this maybe with this. Let's say, let me do it in a different color. Let's say we have kind of this graph, right? And then let's say we're given an array with 2 elements, right? Index, and I know it's weird to index with 1, but that'll make sense kind of in a minute when I get to another part of this example. right? If this had, if we think of this, the amount of elements as maybe dimensions in like a sample space, right? We come up with something like this, where this line is where x equals x maybe sub 1 equals x sub 2, right? And maybe this is x2, it's not equally 2, and this is x1, right? Where this array equals x, or the x array is that. I think this line, so let's say we had like 3 in here, and then we had another 3. This kind of fails the element distinctness because, you know, depending on kind of the scale of this graph, 3 would maybe be there. And so what this shows is that we essentially have 2 spaces, right, where, where points can be, right? So we have like a point maybe here, right? And then that would be what, like 1, 3. Then we can have kind of the inverse point, I guess, here-ish, which would be 3, 1. And anywhere in this space, and this gets projected out kind of each direction, and then really these planes are kind of out in each direction. I'm sorry, not planes, these spaces. Jumping ahead of myself a little bit. So this is in 2 dimensions, right? I think for fun, maybe it's kind of cool. Well, one more thing, so we can note that if we have an input, for input to maybe kind of space, call it space, we have for 2 dimensions, 2 length of 2, whatever you want to say there. We have 2 spaces where we can have valid data, right? And then it'd be hard to draw, but I grabbed this from, I think the website's called GeoGebra, maybe. If you kind of Google it, though, it's kind of a fun website to play around with these 3D planes, right? These are the equations I also brought in. They should be kind of obvious, but let me switch maybe to white ink. Something kind of cool here is if you kind of think about the previous example, this would maybe be, what do we call it? Was it x1? And then this plane, or this axis would be x2. Now we got this third depth axis now, which could be x3, right? And so this would be the input if we had maybe like a 1, 2, 3 array, right? Come on. And then each of these planes, the red plane would be something like x, where x1 equals x2. So like these 2 variables match maybe. I believe green could be, I think it's x1 equals x3, and then maybe this kind of blue plane is x3 and x2, right? Which are these kind of equations over on the right side. I thought it was cool too if you zoom in kind of and stare down the barrel of one of the axes, you can see kind of that slope line of slope 1 in respect to each kind of axis that's where the other 2 variables would match, because if you had something like 1, 5, 1, right, that would be on one of those planes, and then that would then fail the element distinctness problem. I did try to visualize this in 4 dimensions just to see, but it gets kind of useless from there. It was nothing really interesting. This is kind of where it gets important. This stuff I just thought was interesting, but if we look at it from, we're looking down kind of from this angle. It's a little bit hard since I can't spin this around, but that's what this angle is. We're kind of looking down those 3 planes. But notice those 3 planes divide up into 6 total spaces, right? And then these are kind of the planes, if you can see them, kind of going out past the axes markers. So I wonder if I actually can I do 6 pastel colors? That'd be kind of pretty. So notice though that this now divides it into 6 3-dimensional spaces that we can have data in, right? And then up top, I love the seafoam color, is where we had just 2 for an input of 2. I don't know if it's starting to become obvious, and maybe we should draw the table out again. So for 2 inputs, right, we had 2 spaces. Now let's do input again, and spaces, or space maybe. Let's leave space maybe for 1 this time, right? 2 is 2, 3 is 6, right? Now that we kind of have our head around maybe the idea here, let's prove 1 real quick. I think it's kind of cool to see if you have an array of length 1, dimension 1, where that, you know, what does this space, you know, we've talked about kind of going from 2 dimensions to 3 dimensions. What's going down to 1 dimension look like? Well, if we maybe use set notation, right, and we say x such that x, really we can put any number here, right? So x is an element of, let's see if we can do this kind of clean, right? Of all real numbers, right? Because if you think about it, in this array of 1 dimension, you can put a positive number, you can put a negative number, you can put 0, and then kind of scale it out. So really the space is just a space of all numbers, right? But it's 1 space of everything. So 1 is 1. Like I said, I tried to visualize this in maybe 4 dimensions, but that was a little bit tricky. You'll have to take my word for it. But 4 equates to 24 kind of unique spaces, and maybe it's a little bit more obvious now, but that our input is in, and then the kind of output is in factorial, right? And what this means is that what we've just proven is without sorting how many possible outcomes, or even really independent of sorting, that given an array of some length, how many possible outcomes or permutations can that array have? And kind of here's another kind of bit of stuff I pulled from the internet, just kind of as an example. Let's say we have x, just to get this explained real quick. X5, we use 5, 7, and 3 up top, I think. And then the index is up here. Index is 1, 2, 3. And then that's based off of this tree, and I'll kind of explain that. This tree is kind of asking at each root is index, so like x sub 1 less than x sub 2, right? And then we'll kind of branch off in each direction. This is kind of an easier way to view that higher dimensionality, because this is dimension for length 3 or 3 dimensions or whatever, right? And so let's say, okay, let's just go through the example, right? We do 1 and 2, compare index 1 and 2. I find it easy just to write out that 5 and 7, what symbol goes between the two out of these two kind of choices, that binary choice. 5 is less than or equal to 7. So we'll come down this node. Notice we've cut out this whole subtree, right? Because this is every place that index 2 can come before index 1, which wouldn't make sense. In a sorted kind of array, you'd never have 2 come before, or 7 come before 5, right? So you can have like index 2, some stuff, then 1, right? 2, then 1, then some stuff, 2, some more stuff, then 1, then some stuff, right? And that's what we see here. We see 2, then 1, then some stuff, 2, some stuff, then 1, some stuff, 2. And when I say some stuff, I'm just kind of keeping this broad. If this was to be expanded for a higher dimension. What's next? Okay, so we're here. Now we want to compare index 2 and 3, so 7 and 3. Well, 7 is bigger, so We'll come down this route. Notice again, now we've cut out that whole subtree. Same issue anytime this cuts out any permutations where 2 comes before 3. And then finally, we need to sort out 5 and 3, right? Index 1 and 3. 5 and 3, well, that opens to 5, right? So now we come down this tree, and we've cut out this whole subtree, right? Now, the triangles are to represent whatever, if this was a higher dimension, whatever bigger subtrees these would be, right? Now we end up here. This is the order of elements, right? So element 3 is coincidentally also 3. Element 1 is 5, and element 2 is 7, right? So that's kind of how we get to our permutation of the kind of node we want, not doing a direct comparison kind of style sort. And I think this also kind of helps prove we'll have n factorial leaf nodes, possible outcomes, right? And then we simplify our sample space by 2 every time we make them one of those decisions. We either go left or right, and that cuts our sample space in half. And we have n factorial nodes. And so we want to figure out the height of this, right? Because this is the path we have to take to kind of solve this problem. What is the height of this tree for some general thing? So the height just equals log of n factorial, right? And this kind of permutation concept could also be solved with combinatorics. You know, if we were to go, well, we have n choices for the first element, and then n minus 1 choices for the next element, n minus 2, so on until we have 1 choice for the final element. And so I also brought in some log rules kind of from the internet over here too. And we know with this kind of log factorial thing that we would be taking log base 2 of n, and then we could kind of break it up into log base 2 of n minus 1. And I guess this would be like n minus 1 factorial, and you keep breaking it up that way, all the way down to log base 2 of 1, right? From here to kind of finish out this proof of how far we have to travel, if we think about this visually, what I guess log natural or log of n kind of, or log of x in this case, would look kind of like this, right? But now we're summing up everything from 1 to n, right? And that's effectively taking the area under the curve, which screams integration to me. So let's do, we want to take the integration of, well, it's going to be bounded because we want to go from 1 to n, right? So we'll do the integral from 1 to n, right, of just log n, right? Yeah. And so in respect to n, I think we'll need integration by parts. Let me grab this, maybe copy. And so I'll write that kind of that integration by parts formula down in case, I'll just do int by parts. In case anyone's calculus is a little bit rusty, it's what I think there's a few ways to write this. I've learned with u and v. Maybe keep it general. uv minus what's it, u prime v, because the hope is that we're trying to simplify this thing and not make this thing any more complicated, right? We'll need maybe some log identity. So let's do the derivative of natural log. I think that'll be useful. Is what, 1 over x, right? Then kind of the inverse of that, dx, dx, log base b of x is 1 over that x log, I'm sorry, natural log of that base, right? I think that's about all we'll need. So let's go ahead and try to solve this, right? So let's see. We need our u prime, v prime, and v. And then there'll be an implied 1 here, kind of for just by, since we're using parts, we need that u and v. Log base 2 of n, and then this will be that 1 over, and I mean, I've been stating 2, but since everything's computer science right now, it's ln of 2, right? Then 1, and then this goes to n, right? And then now it's just plug and chug. Yeah, so we get that n log base 2 of n minus indefinite integral from 1 to n. And then this simplifies kind of nicely, right? We have n ln of 2 dn, right? These n's cancel out. They're just variables. So then maybe rewrite this one more time before we kind of solve it. N minus 1 to n of, well, really ln of 2 dn. It has no n term, and we kind of know this is just a constant. We don't really care what the constant is, right? So if we were to solve this out now to n minus, I'll put it in brackets, right? Let's just call it c, right? C n from n minus to 1, and then what, top minus bottom, so cn minus c, yeah, okay. And then finally, kind of do it on this next page, n log, so it's just to write it out, we have n log n minus some cn plus some c, and then kind of as before though, this is the domineering term. This constant might, you know, if I was on a computer, I'd maybe graph this out on Desmos for fun just to see it, but you know, this is kind of the domineering term, and so we'd write that the runtime is n log 2 of n, right? And if we remember from what we were trying to prove in the element distinctness problem, is we're trying to prove that it's less than, how many pages did I use? Less than n log n, and we've just proven that using this kind of tree method in the best case to try to get to our answer without that kind of comparison nature of the sort and everything, the best we can essentially do is n log n. So sadly we weren't able to prove that we could do the element distinctness problem with this parameter in less than n log n time. Thank you.